The concept of personalized nutrition is no longer just a futuristic idea. It is rapidly approaching practical reality, with the gut microbiome emerging as one of the most promising biomarkers for predicting how individual bodies respond to different foods. Advances in sequencing technology and bioinformatics have revealed that our intestinal microbial communities are highly individualized, influencing everything from glucose metabolism and lipid handling to inflammation, satiety, and even mental well-being. By analyzing a stool sample, scientists can begin to identify which microbial strains dominate a person's gut, the functional capabilities of these microbes, and the metabolites they produce. This information opens the door to tailoring dietary recommendations in a way that is far more precise than generic guidelines, potentially optimizing metabolic health, weight management, and disease prevention on an individual basis. Clinical studies and pilot trials have already demonstrated that microbial composition can predict glycemic response to foods with surprising accuracy. For example, two individuals might eat the same carbohydrate-rich meal and experience dramatically different blood sugar spikes, largely due to differences in the abundance of SCFA-producing bacteria, bile acid metabolizers, and polyphenol metabolizing taxa in their guts. Personalized dietary strategies can then be developed to enhance the growth of beneficial microbes, reduce populations associated with inflammation or insulin resistance, and improve overall metabolic outcomes. In this context, foods like pistachios become particularly interesting because of their multifaceted, microbiome-friendly properties. Pistachios contain a unique combination of fermentable fibers, monounsaturated and polyunsaturated fats, plant protein, and polyphenol, all of which interact synergistically with the gut microbiome. For individuals whose stool sequencing reveals a low abundance of SCFA-producing bacteria such as Roseburia, Lactospiraceae, or Bifidobacteria, pistachios could serve as a highly targeted intervention. The fermentable fibers in pistachios feed these beneficial microbes, promoting butyrate and propionate production, while the polyphenol are metabolized into bioactive compounds that reduce oxidative stress and systemic inflammation. The unsaturated fats further enhance microbial function and improve lipid metabolism, creating a nutrient environment that maximizes the growth and activity of bacteria critical for metabolic health. Beyond SCFA production, pistachios may benefit individuals with specific microbiome patterns linked to glycemic instability. People with a higher proportion of opportunistic sugar-metabolizing bacteria may experience exaggerated glucose responses to refined carbohydrates, while those whose microbiomes are enriched with fiber and polyphenol-fermenting microbes generally achieve better glycemic control. Incorporating pistachios into the diet of individuals with less favorable microbial profiles could help shift the ecosystem toward a more resilient, metabolically active state, reducing postprandial glucose spikes and enhancing insulin sensitivity over time. The potential of microbiome-guided dietary personalization extends far beyond blood sugar control. Gut microbes influence appetite regulation, lipid metabolism, immune function, and even mood through the gut-brain axis. A stool-based analysis could therefore inform a comprehensive, individualized eating plan that incorporates foods known to nurture beneficial microbes while minimizing those that promote inflammation or metabolic stress. Pistachios, with their combination of fiber, polyphenol, and unsaturated fats, represent a versatile, low-risk intervention that can be easily incorporated into a personalized plan, whether as a snack, salad topping, or component of a balanced meal. Future applications of this approach may include dynamic feedback loops, where gut microbiome sequencing is paired with continuous glucose monitoring, wearable metabolic sensors, and dietary tracking apps. Such systems could identify real-time responses to foods, allowing for precise adjustments that optimize both microbial health and metabolic outcomes. In this vision, pistachios could be recommended to specific individuals at strategic times of day, such as a pre-bedtime snack to stabilize overnight glucose or as part of a mixed meal to support microbial fermentation and SCFA production. Over weeks and months, these targeted interventions could gradually remodel the gut ecosystem, creating a self-reinforcing cycle of improved microbial diversity, enhanced metabolite production, and better systemic health. In summary, personalized nutrition based on stool microbiome analysis represents a paradigm shift in how we think about food and health. Rather than relying on generic dietary rules, Future strategies could leverage individual microbial signatures to optimize metabolic function, satiety, and inflammation control. Pistachios exemplify a food that fits perfectly into this model. Their fibers, polyphenol, and unsaturated fats provide multiple avenues for enhancing beneficial microbial populations, producing SCFAs, and supporting metabolic resilience. For individuals with specific microbial profiles revealed through stool sequencing, pistachios could become a cornerstone of a personalized nutrition plan, illustrating how thoughtful food selection can be tailored to the unique ecology of one's gut to achieve measurable, lasting health benefits.